Okay, so what I'm going to talk about is some of the work that we've been doing in my group in trying to make serverless become the future of the cloud, right? The work that I'll present really is a wide collaboration with folks from MSR, researchers and students from several universities, Stanford, Berkeley, Purdue, Princeton, Cornell, and the Azure Functions team. So let's jump right into it. Um, Before saying anything about serverless computing, we really have to define what this term means. It's highly overloaded. So what it means to me is a cloud computing paradigm or abstraction where users don't have to specify um, the number of VMs that they want. They don't need to configure the resources. They don't want to reserve resources and so forth. And they get the notion of infinite and fast scalability from not consuming any resources at all to consuming as many resources as they might want, and all the way back as well. And also very importantly, that they pay per use. They pay per resources that they actually use versus resources that they might allocate. So the most popular offering of serverless computing today is called Function as a Service, or FaaS, which essentially consists of bounded time functions that have no persistent state across invocations. And for that reason, we call them stateless functions. If we want any state to persist from one invocation to the other, we really have to use some sort of remote storage service or a remote queue of some kind. The functions execute when they're triggered, and there are a number of different triggers, the most common being HTTP requests, timers that go off periodically, and event or message queues. And basically the paradigm is very simple. The user uploads their function code, they get an endpoint from the FaaS provider or the serverless provider, and then they execute. And for the rest of the talk, I'm really going to talk about FaaS and serverless interchangeably. So whenever I say serverless, you can think of serverless, function as a service. So another way to think of serverless is as an evolution of the cloud. Let me bring up my laser pointer here. So in this table here, I'm showing you on the left here a number of different characteristics of these different stages of evolution of the cloud. Things along the lines of, what is the unit of scaling? How long does it take to initialize? How does scaling work? Typical lifetime, the payment model, and where state is stored. And each of these different stages here is a different stage in this evolution of the cloud, right? So we started out, if maybe the more senior folks remember this, the hosting centers where enterprises deployed physical servers to a hosting center that would operate their servers. And here you had initialization times along in the order of days, and scaling was based on buying more hardware. And the typical lifetime was years for those servers. The payment was per servers, and the state could be anywhere. Right? Then we moved on to what we think of today as the cloud, with VMs being deployed to the cloud. And initialization times became a lot lower. Instead of buying new hardware, we would allocate new VMs. Lifetimes for those VMs are on the order of hours. You pay per allocation, and the state, again, can be anywhere. Then we moved to containers, and finally we're now at functions, or function as a service, where the unit of scale is really a function. We started with a server, and now it's a function. The initialization time is a few seconds at most. Scaling can be from 0 to many, and it's done automatically. As you see later, typical lifetimes are very short in this range here. People pay per use, like I said before, and the state, like I mentioned, functions are stateless, so the state has to be stored elsewhere. So you see here, functions can also be seen as the latest stage in the evolution of the cloud. And this is what we're going to be talking about today. So what has been said, there's a lot of attention and hype around serverless. And you can tell that from the articles that have been written in the IT press about serverless. And many of them talk about serverless being the future or being the future of software and apps and so forth. So it has gathered a lot of attention in the IT press. Similarly, in the research community, serverless has been receiving a lot of attention. The fact that I'm giving this talk on serverless should also indicate that. And there have been many papers, and one of them, sort of in particular, an early paper from Berkeley, actually stated that they predict that serverless computing will grow to dominate the future of the cloud, right? Pretty much along the lines of what our group is trying to do. And finally, another way to see how serverless has been growing is with respect to the number of platforms, both hosted and installable, that have been created so far. So AWS Lambda was the first one to be introduced, but there's also, Azure Functions, Google Cloud Functions, IBM Cloud Functions, and so forth. And in terms of installable platforms, there are many today that are, open source, for example, like OpenWhisk, and have been used extensively in research as well. So as you can see, there's a lot of momentum behind serverless in many different directions. Now, the question, an interesting question is, what are people actually using serverless for, right? It turns out that what they're using it for is many very useful things, but typically simple things. So for example, extract, transform, and load workloads, IoT data collection from sensors and those kinds of things for like simple processing of those collected data, collected sensor readings, different kinds of stateless processing like image and video encoding and so forth. Using it as APIs for mobile and web backends. So a fairly limited number of simple applications. But there have been promising explorations in terms of, for example, many efforts along the lines of parallel computing, like for example with MapReduce and PyRen, sort of MapReduce for Python workloads. NumPyRen, similarly for linear algebra. Burst parallel function apps, like for example, parallel builds and so forth. So these have been typically explored, starting in academia, but have demonstrated positive prospects, right? That there's the potential to increase the scope of applications here. And the reason, or some of the reasons why serverless hasn't become more broadly used for a wider set of applications main reason is the fact that functions are stateless, like I mentioned before. So any state that needs to be persisted needs to use some sort of remote store. And because of that, high latency has been an issue. Not only because of high latency and the access to data, but also in this phenomenon that we call cold start, which basically means that when we need to execute a function, before we actually execute it, we have to prepare it to be able to execute. So we need to bring into memory, have to create a container, have to bring in the function runtime, have to bring in the function code and so forth. And that takes time. So that has been a major concern for actual users of serverless offerings today. Another one is limitations in I/O bandwidth. And oftentimes you might get limited by the bandwidth of the underlying VM where the serverless container is created. Or you may be limited because other containers running in the same VM are consuming a lot of the bandwidth of that VM. So that has been an issue as well. And finally, an important one is that communication between functions hasn't been really considered the first class thing. And most of the time, there's no way of even addressing another function to be able to communicate with it. So that has been a problem, despite the fact that some efforts recently, like durable functions and step functions and so on, are trying to create some sort of orchestration environment for us to run functions and function pipelines and so forth. So these are some of the limitations that caused limited applicability so far of serverless. But there's also, we should think about also for the serverless provider, what some of the challenges have been. And note here that I'm drawing a difference between the serverless provider and the cloud provider, right? The serverless provider is the entity that's supposed to allocate resources from the cloud provider. Typically, those resources are VMs or perhaps even bare metal servers where they run their fast service. Right, so the serverless provider has to worry about a lot of the things that users don't have to worry about. Right, the serverless provider has to provision these VMs, have to do scaling, to allocate them, to guarantee security across customers, has to provide the illusion of infinite scalability, has to trade off, cost and performance, because obviously, we can maximize performance for starting functions, for example, by not having cold starts, instead having warm starts, by keeping all the functions in memory all the time, right? But obviously this would impose a very high resource cost, right? Similarly, there's a trade-off between cost and security, where if we use multi-tenancy and have many customers, the functions of many customers running in the same VMs, there could be security issues. So spreading them out across VMs is also a possibility, but again, there's a high cost penalty. So the serverless provider has to really optimize resource usage via tight packing and multi-tenancy so that it can manage its costs. And really sort of not being able to do that in such a fiercely competitive market is going to end up meaning that Amazon is going to eat everybody's lunch, right? So what we're interested in our group is in addressing the limitations that I mentioned in the previous slide and these challenges that the serverless provider faces. So how do we think about, how do we organize in our heads, how serverless should evolve, right? So today, we are at a stage where there's the serverless workload is a fairly small fraction of the overall cloud workload. As I mentioned before, typically it's simple apps that are getting implemented, and the price that's being charged to customers doesn't really reflect the cost that the serverless provider needs to pay. So in one dimension, what we want to do is broaden the scope of applications that can execute efficiently in the serverless paradigm. And for that, we need to improve performance by looking at new abstractions, new systems, new tooling, and potentially even system and hardware support. And also look at programming model improvements. Like I mentioned before, durable functions and step functions have made programming model improvements to be able to use to orchestrate functions. Our group is mostly a systems group, so we don't go too deep into programming model research, but we do a lot over here in improving performance. So in the other dimension, what we would like to do is make sure that we improve resource efficiency and reduce costs for the serverless provider. So what that involves is things like predicting workloads and being able to minimize resource usage based on those predictions, or run functions on spare resources from the cloud provider so that the resource provisioning or resource allocation becomes a lot cheaper, and running tiny VMs so that we can maximize multi-tenancy. And we think that only after we sort of have been able to address these two and make significant progress in these two dimensions will we get to a future where serverless is truly the future of the cloud. So what I'm going to talk about in the bulk of my talk is some work that we've done in terms of predicting workloads and using those predictions to minimize resource usage, and a new abstraction that we created, a new data structure that we created to optimize cold starts. And later on, when I'm talking about sort of current and future work, I'll talk about other aspects of improving efficiency and improving performance. Okay, so here's the roadmap for the rest of the talk. I'll start with a workload characterization from Azure Functions. It's really tough to try and improve things if you don't understand what they are at this point. Obviously, in the future, as we broaden the scope of applications, the workload is going to change, but we felt like we needed to understand what's going on right now. And after that, I'll show you this data structure and policy that we've come up with to, at the same time, reduce the number of code starts and the resource usage that's required to keep code starts low. And we do that via workload prediction as inspired by a workload characterization. Then I'll talk about, what we're doing sort of going forward and what we're planning to do, and then we'll conclude. So, so let me start with the workload characterization. When we started looking at understanding the workload of real serverless providers, we realized that there really weren't any good characterizations out there that were from the point of view of the provider. There were many works where users were trying to reverse engineer what was going on in the provider. So we decided to do an actual study from the provider's perspective. So we took a look at 2 weeks of the entire workload of Azure Functions in July 2019. And this came out as a paper in ATC 2020 that got the community award. And the reason why it did it is that we made traces, representative traces of Azure Functions available for the community to use. And you can find them here, and you can find the reference in the paper as well. So before I explain to you sort of what types of questions we were trying to answer, let me tell you a little bit of Azure Functions, because that's where we got the traces from. That's where we got the data from. In Azure Functions, functions can be written in many languages like C#, JavaScript, Python, and so forth. And functions have the triggers that you would expect: HTTP, timers, event queues, message queues, remote storage, and so forth. But the key aspect of Azure Functions that we need to talk about is the fact that in Azure Functions, functions are actually grouped into applications or apps, as I'll talk about throughout the talk. So the app is the unit of resource allocation and scaling. So when we need, the load is growing and we need an extra instance, it actually is an extra instance of the full application or the set of functions that form that application. And so if I take a cold start and I'm going to bring in an instance of a function, I'm actually bringing in the whole application to memory. So what are some of the questions that we were trying to answer with our characterization? Here is a pretty large set, like how frequently functions are invoked, what are the types of triggers that functions use and how often they use them, how long functions take, how much memory do they consume. So I'm not going to have time to go over all of these, so I refer you to the paper. What I'll talk about now is just these three, right? How frequently functions are invoked, how long they take, and how much memory they consume. So let's start with the number of invocations per application. And this data here is for a representative subset of the workload. You can read the paper for the details of how we define this subset. But let's look at what this graph shows. So on the x-axis, I'm showing you daily invocations per application. And this is a cumulative distribution. So this is the fraction of applications, cumulative fraction of applications. So what you can see here is that on this side, we have the less frequently invoked applications, or sometimes I call them the least popular, the most unpopular applications. And these are the most popular ones on this side, right? And a first observation that's very interesting is that there's an 8 to 9 orders of magnitude difference between these two ends, right? And so this makes it very clear that trying to optimize things for the whole range is a challenge, right? Another thing that this graph shows is these vertical lines across the graph actually means interesting average inter-arrival times between invocations. So this is 1 second, 1 minute, 5 minutes, 15 minutes, all the way to 1 day, right? So these applications over here are invoked on average less than once a day, right? So if we look at this group here of 45% of applications, they're invoked on average less than once per hour, right? So they're fairly unpopular applications. If we look at this group, in this group, the yellow, I colored it yellow here, including this other group as well, we see 82% of applications, they're invoked on average less frequently than once a minute, right? And there's a 12% in this red area of applications, they're invoked more frequently than once per minute, okay? So let's look at this from a different perspective. So what I'm doing here is I'm flipping those two axes and I'm plotting the percentage of most popular applications from most popular to least popular, and accumulating over here the fraction of invocations, right? So and I use the same color scheme as before, right? So the red area here is those 18% of applications that are invoked very frequently, and the yellow and green here is the 82% of less frequently invoked applications. So what's interesting here is that those 82% correspond to only 0.4% of invocations, right? Whereas the other 18% correspond to 99.6. So the vast majority of invocations really come from these 18% of applications. And yet there are a lot of customers here behind these 82% of apps, right? So we need to make sure that we optimize their performance, even though the percentage of invocations that they correspond to is extremely small, right? So here's another look at the invocations within applications. And this, what I'm going to try to show here is that just looking at an average doesn't really mean very much, because as you look at different applications, and I'm showing you here on the x-axis, I'm showing you the arrival time of each invocation. Each of these dots is an invocation. And on the y-axis is the inter-arrival time between invocations. And don't worry if you can't read this thing in detail. My point is to show you that, across different applications, they can be very heterogeneous, right? You see, some applications have pretty regular invocations, whereas other ones can be very bursty. And the variety of applications is pretty wide. And what this suggests is that, anything that sort of applies to all functions equally, or all applications equally, is not likely to work very well, right? Because the characteristics are so different. And even within the same application, there might be variations. So now let's talk about the amount of memory that these different types of applications would consume. So here I'm showing you a graph. On the x-axis, I'm showing you the fraction of least invoked applications. So these are invoked the least, these are invoked the most. And this is the cumulative fraction of total memory that they would consume if we were to keep them warm all the time. We'd keep them in memory all the time. So the red curve is the allocated memory, but let's focus on the physical memory consumed by these applications. Again, I'm showing you the 82% here in yellow of applications, right? 82% over here. They would consume 40% of the physical memory if we were to keep them in memory all the time. And similarly, if we were to keep around 1% of the invocations, which would translate to about 90% of the applications, they would consume 50% of the physical memory. So clearly, these are applications that are invoked very rarely, but would consume a significant fraction of resources if we were to keep them in memory all the time. So we got to be able to do better than that. So now let's look at function execution durations. Here I'm showing you time on the x-axis and a CDF of the duration times. And the different curves just mean the minimum, average, and maximum duration of the invocations, and a log normal fit that I'm showing here because it's so good for the average. So the executions tend to be short, right? 50% of the executions, this point right here, are really take less than 2/3 of a second, right? Very short. And 75% of functions run for less than 10 seconds. Again, very short, right? So this shows that functions tend to be short. And the important aspect of that is that those durations are actually comparable to code start times, meaning that we really need to optimize for code starts, because otherwise executions become essentially dominated by the overhead of code starts. So to summarize the takeaways from at least these three angles that I showed you here, invocations are highly concentrated in 18% of applications, but we need to optimize for the other 82% as well, because those represent a large number of customers, or the larger fraction of customers, right? And we need good performance for these applications, but we have to do it at a lower resource cost. We can't just keep things warm all the time. The arrival processes, or the invocation processes, are highly heterogeneous across applications, meaning that techniques that try to manage resources should really be used on a per app basis if possible. And finally, execution times are short, so code starts cannot be neglected. We made traces available for everyone to do their research and study them, but yet there's a big need for real workloads. And this is something that we're facing and trying to address, but it would be great for the community to try and create sort of these types of repositories where we put real applications, not just traces of their invocations. Okay. So now that I've covered the workload characterization, let me talk about this code start management policy that we created to reduce code starts at the same time as reducing resource usage via workload prediction. So what is a code start like? what really is involved in a cold start. So here I'm showing you a cartoon or a figure showing what happens in Azure Functions, right? The Azure has to allocate resources to or Azure, the serverless provider, Azure Functions, has to allocate the worker to execute, has to reset the function runtime, has to load the function into memory, and then only then does the code run. The same process happens for OpenWhisk and AWS Lambda and all the other serverless platforms. So there are two approaches here to manage code starts, right? It's a potentially expensive operation, right? So there are two approaches. One is where we make code starts faster by optimizing this process of getting a function ready to execute. And the other one is to reduce the number of code starts to begin with. And this is the approach that we take in our work, or we've taken so far. So let's think about this trade-off between the number of code starts and the amount of memory that we're wasting by keeping the function in memory without actually executing anything. So if you plot this as a two-dimensional graph, and we assume, well, let's keep all functions in memory. Let's look at the two extremes, right? Let's keep all function instances in memory indefinitely. So this would give us a very small number of code starts, just the first use of the function. But the amount of wasted memory would be very high. If we were to look at the other extreme, where we remove the function instance every time it finishes executing, we would have a very large amount of code starts, but the memory wasted would be zero, right? Because as soon as execution ends, we would unload the function from memory. So clearly there's some sort of Pareto frontier here that we can try to optimize by pushing it towards the origin of this graph, right? And this is something I'm gonna get back to later on. And show you how our technique has been able to do that. The question that now you might be asking is, well, what do serverless providers actually do today? Well, it turns out that the way they solve this trade-off is by unloading an instance after some number of idle minutes. And in Lambda, it's 10 minutes. In Azure Functions, it's 20 minutes, but it's the same idea, right? After some amount of time that the function has not been executed, just unload it from memory, right? And we call this the fixed keep alive policy, right? So how does it work? Here I'm showing you an example of an application or a function that was executed the first time at this time here, say time 0. And then the next execution, because we're assuming a 10-minute fixed keep alive here, would be a warm start, right? Because this is 10 minutes away, so this would be a warm start. Then if another one came another 8 minutes away, it would be another warm start, and so forth, right? However, if the application, instead of having these 8-minute invocation times, if it had 11 minutes, then every invocation would be a cold start, right? Because 11 is more than the 10 minutes of the fixed keep alive, right? So clearly it doesn't work well for all applications. Another problem with it is that it's actually wasteful, right? Because in between these two invocations here, I got a bunch of memory there that's being reserved for this function, and it's not being used for anything, right? Because there are no invocations of the function going on in these intervals here. So what we came up with was a code start management policy that we call the hybrid policy, that tries to reduce the number of code starts while at the same time keeping resource usage very low. And we do that by using per application workload prediction, right? As I mentioned in our characterization, clearly doing something for all applications in the same way is not going to work well for most of them. So some of the principles that we use in defining exactly what this function should be, this technique should be, is that we want to adapt to each application's invocation pattern. And we use a standard fix keep alive policy until we find a pattern in the invocations. So while the pattern is unclear, we just use something standard so that we don't hurt anything. But when the pattern becomes clear, then we start to do what we call pre-warming. In other words, if the idle time between invocations is large enough, we unload the function from memory and warm it up just before the invocation is going to come, right? So this is what we call pre-warming. And after we bring the function to memory, we keep it alive for a little bit so that the invocation has time to arrive. And because we wanted to build something that could be practically deployed, we had to come up with a very lightweight implementation for this approach. And it turns out that we created a data structure that is very lightweight and very simple and very practical to represent this, to learn these idle times, to identify these patterns, right? So let's go back to our example. Let's say a function invocation arrives at time 0, and then the next invocation comes 8 minutes later. So this is the idle time between the two invocations. And what we do is we store the fact that the first idle time was 8 minutes in a histogram, right? So the idle times are on the x-axis and frequency on the y-axis. So another invocation arrives 8 minutes later, for example, and we again record another invocation with 8 minutes idle time. So we keep doing this for all the invocations of the application, and we may end up, or the function, depending on whether we're talking Lambda or Azure Functions, and we may end up with a histogram that's like this, right? There are invocations that come with idle time 7 minutes, 8 minutes, and 9 minutes. From this, we can define what the pre-warm is going to be, right? We know that by looking at this histogram, there are no invocations that come less than 7 minutes from the previous invocation, right? So we can unload the application for this amount of time. And this also shows us that the keep alive can be just 3 minutes, right? We know that idle times will be either 7, 8, or 9 minutes, right? So this is a very compact way of describing these two key parameters of the policy, right? So the question then becomes, do I really not need to have a whole histogram? Is it not enough to just know the minimum, say 7, and the maximum, say 9, of the idle time distribution? Turns out that not really, because we want to play the following trick, right? We want to exclude outliers, right? So what we use in our experimentation is really we cut off the histogram at the 5th percentile so that we don't reduce our pre-warm duration unnecessarily just because of rare short idle times. And at the same, in the same way, we want to cut our keep alive over here on this side so that we don't have an excessively long keep alive. And we put this cutoff at the 99th percentile of the idle times. So with this, we have to define now how many of these bins we're gonna keep for each histogram, right? So we vary this, but we settled on 4 hours, which is 240 bins and represents basically 1 kilobyte of storage for each application. So but what happens if, we have invocations that have idle times longer than 4 hours? Well, we keep the number of those invocations and when they occur over here in terms of out of bounds invocations. And when that number grows significantly, then we start to resort, a histogram would be inefficient, and we resort to time series analysis. The nice aspect of this is time series analysis tends to be a little more expensive, but because these functions are invoked very rarely, we can actually afford to run more complex predictors. And we use ARIMA forecasting in this case, as I'll show you in the next slide. So putting these two together, the way the hybrid policy works is whenever a new invocation comes, we update the idle time distribution for that application. And then we check the number of out of bounds idle times. If the number is large, then we resort to time series. Oops, sorry, went the other direction. If the number is not large enough, so we check for a pattern. If there's no pattern, a clear pattern yet, we are conservative and use a fixed keep alive policy. But if we have seen a pattern, then we go and use the histogram for that application, right? So now let's look at what happens. Remember the cartoon I showed comparing or trading off code starts for memory usage? Here's a different view of that type of graph. So here I'm on the x-axis, I'm plotting the third quartile of application code starts in percentage. And over here, I'm plotting the normalized wasted memory time or memory hours normalized to the Amazon Lambda approach of 10 minutes of fixed keep alive. All of these are fixed keep alive durations from 5 minutes to 120 minutes. So for you to really understand how to read this graph, let's look at a couple of points in it, right? So this one here shows that with 5 minutes fixed keep alive, 75% of apps experience 65% or fewer code starts, right? Similarly, up here with a 120-minute fixed keep alive, 75% of the apps experience 20% or fewer code starts, right? This is the third quartile. This is why these are 75% of apps. So now, if we now look at what the hybrid policy does, it produces a Pareto frontier that's substantially better than the Pareto frontier that the fixed keep alive produces, right? And the way to read this figure is that, let's take the 4-hour keep alive, for example, right? No, sorry, the 4-hour hybrid policy. It achieves the same code start percentage as the 100-minute fixed keep alive policy, but using only 2/3 of the resources, right? So we can achieve a very low code start rate by using even less resources than the fixed keep alive policy would. A very long keep alive policy, one that consumes a lot of resources. Another way of looking at this is that we can achieve less than half of the code starts than less than half of a 10-minute fixed keep alive policy using 15% fewer resources than what that policy would use. And we confirmed these results in production as well. At both production and OpenWhisk implementation. But the production results so far have shown that 36% of the HTTP triggered applications are being pre-warmed with a 97% accuracy in pre-warming. So the results have been really good from the production deployment that we have in Azure Functions. So this shows that it's possible by sort of being aware of the different characteristics of applications to come up with policies that do a good job of reducing the number of cold starts and resource usage at the same time. So now let's talk about going forward. Sort of some of the current work that we've been doing is along the lines of, first, let me talk about sort of running on spare resources to improve efficiency. We've realized that a serverless platform, in terms of how functions execute and their duration and so forth, they lend themselves nicely to the use of spare resources that might come and go in the cloud provider. So we're actually looking at using Harvest VMs, which we're proposing in OSDI 2020 in a few months, so these Harvest VMs, essentially what they do is whenever they land on a machine, they expand and contract to take up all of the unallocated resources of that machine. And because all of those are spare resources, the cloud provider charges a very low amount a very low price for those extra resources. So this is a way that the serverless provider can use to reduce its costs significantly. The trick then becomes how to adapt the scheduling of the functions to the availability of resources. And we have a prototype implementation of harvesting aware OpenWhisk as well. So another thing that we're looking at in terms of improving performance is, we need fast state, right? As I mentioned before, sort of having to access remote state is a big problem. So we are looking at a cooperative in-memory cache targeting large state. And the cache, is actually tied to applications, and we scale it according to both compute and data. And we use the pre-warming approach as well, so that we bring it to memory in the background. Another thing that we need is sort of efficient task parallel computation, and we're looking at running the Dask Python library that runs task DAGs and sort of figuring out how to optimize it to use large data. And finally, we're looking at performance prediction and quality of service. And some of the recent work in the group has shown that we can predict the performance of function pipelines, and using those predictions provide differentiated levels of service. Sort of going forward, we're thinking about sort of the management of multi-tenancy and how much oversubscription can be used and these kinds of things when we have tiny VMs for multi-tenancy, so that we can put them together tightly without security concerns. So we also are looking at a potential system and hardware support along the lines of perhaps locality aware cluster scheduling, on-node container scheduling, for example, trying run to completion instead of time sharing, given that the executions are short, looking at hardware support for container startup, cross-container communication, and so forth. So all of these areas have received some attention, but we are we want to join those efforts as well in the near future. Finally, we're looking at new tooling as well in terms of tracing and debugging tools, so that we enable sort of more complex applications and can enable optimizations to applications like better scheduling and so forth. So hopefully I've been able to convince you that serverless can be the future, but for it to become the future, we really need to do two things, two main things: broaden its scope and improve its efficiency. And this poses many open challenges, and they're attracting a lot of attention from the research community. And I hope that this talk is contributing to that, because I think there's an enormous opportunity here for both serverless providers to to provide better service and become more efficient, but also researchers to address all of these challenges. Thank you very much. I'd be happy to answer any questions if there are any. How related are serverless computing and disaggregation? Is resources aggregation a solution to serverless limitations? That's a great question. As part of another project, we're also looking at disaggregation and memory disaggregation in particular. It's not a solution to all problems. It could potentially be a solution in terms of reducing the amount of memory that gets consumed. But there are many other limitations of serverless that are not addressed by that, right? So for example, I talked about IO bandwidth limitations. I talked about communication issues, cold starts, right? So all of these are unlikely to be solved by disaggregation, although disaggregation could help with the memory aspect of things. Based on the limitations, serverless computing is not a good option for edge now. But you think, yeah, that's related to the previous question. It's not ideal for the edge now. There's no sort of platform that I know of that's running on the edge, but the same ideas can be used there. I don't see a conflict at all. And finally, regarding the hybrid policy, the bins at the time vary from day to day. Yeah, sometimes things vary. And that's why we keep tracking sort of over time. But oftentimes you see applications that are their patterns keep repeating, right? Obviously the ones that are triggered by timers are very consistent, right? The ones that are triggered by other triggers are not as consistent, have some variation, but oftentimes you can restrict the variation like we did and keep the keep alive threshold pretty short because things are restricted to fairly narrow window of idle times. Okay, next one by Joel. Do customers typically pay for container startup time? That's a great question. And I don't really know what Lambda does. I believe that Azure Functions does not charge for the setup time, the startup time, but I'm not sure. But I can see perhaps people doing it both ways. As long as they are upfront about how they charge, it should be okay. Okay, next one here. Next one. Okay, I have a question about conducting research activities. Do you have any suggestion for research in academia to? Yeah. Right. So this is a question about workloads and related data sets from commercial companies like Microsoft. So in the GitHub site that I mentioned, we have representative traces from Azure Functions. That's a good start if you want to study things like, idle times, function durations, amount of resources consumed, those kinds of things. But if you want workloads, actual workloads, there are some works that have from academia that have involved applications. There's work from Cornell, work from Princeton, where they usually have a small number of applications. It's the workloads come from academia, so it's debatable whether they are representative of what's happening commercially. But that is a real problem, and it's one that we hope to address eventually. We just haven't. And when we come up with a set of of workloads, we'll try to make them available the same way also at that site. But yeah, there's a need for workloads for sure.
I think we can take one more question in the interest of time, at least live.
Okay. All right, one more.
I'm curious actually about Michael Factor's question about unlearning.
Oh, okay. So quick point about just this one here. The question is about the difficulties with communication between functions. And what the questioner here states is correct. The communication has to be done through message queues or remote storage. So let's go to Michael's question. Yeah, great question. So in our paper, most of our experimentation didn't run for long enough so that unlearning was an important thing, right? So the question is about unlearning the histogram so that we don't get influenced by early behaviors that then change over time. So, but in the production implementation in Azure Functions, we collect daily histograms and aggregate them only over the last 2 weeks. So anything sort of older than the last 14 days, we forget. So that's how we unlearn.
Okay, thank you. I'm gonna thank the speaker on behalf of everyone.